Hello everyone, and welcome to this 22-minute Solidworks webinar, Best Practices for Injection Mold Design. My name is Cliff Benling and I'm going to be your host. We're going to jump right in as we have a lot to cover in just 22 minutes. First of all, using the ON24 system, sorry, let me change slides here. If you have any questions, please notice the console at the bottom. If you have any questions, click on the red Q&A button and we'll be sure to answer as many of those as we can after the 22-minute presentation. We stayed on quite a bit late for the earlier webinar to answer questions. We're also going to have some poll questions during the presentation, so those will pop up in your screen. And please answer those multiple choice questions very quickly so we can keep moving forward. Also, please note that we are recording this webinar, and about 4 hours after the completion of the webinar, you'll be able to click the same link from your reminder in the email, and you'll be able to watch the recording at any time. And as I said, we're going to go ahead and jump right into the first poll question, which should pop up on your screen there. Are you involved in the design or manufacture of injection molds? And this is you yourself in your organization, not contracted out. I'll give everybody a few seconds to answer, and then I'll show the results. All right, let's wrap it up. And 62.5% say yes. So with that, I wanted to hand it over to our two presenters today. Peter Rosinski has over 15 years of engineering simulation software experience with roles leading product management and marketing communications organizations. Holds a bachelor and master's in plastics engineering from UMass Lowell. Is currently the senior product portfolio manager for Solidworks Plastics. Matthew Fourcade will be given the product exploration. And Matt has a bachelor's and master's in engineering from Grenoble University in France, and has been with Solidworks over 4 years now, working in product portfolio manager. So I'm going to hand over to Peter. Thanks. It's all yours.
Thanks, Cliff. And as Cliff said, we have a lot to cover today, so we're going to dive right in. Before I get started, I just want to set proper expectations. What we're talking about today, it's in best practices in injection mold design from a plastics point of view. So we're not talking about automated mold geometry creation or anything like that. This is really looking at the best practices in mold design, taking into account the considerations related to plastics themselves. And with that, I would jump right into a brief discussion about some of the most common types of plastics materials. The main groups of materials we want to talk about today are thermoplastics, and within thermoplastics you have two basic subgroups, amorphous materials and crystalline materials. You can see on the left-hand side of the screen I list some common amorphous materials, things like polycarbonate, acrylic, polystyrene, PVC, as compared to crystalline materials, materials like high-density polyethylene, low-density polyethylene, polypropylene, nylons, and others. The reason why it's important to understand that there are these two basic groups of plastics is that they have there's very different properties between both of these two groups, and these are the kinds of things that you have to take into account when you're designing or manufacturing an injection mold. So for example, amorphous materials, because they're transparent in their natural state, they have very good optical properties. You'll see them used in lens applications like automotive taillight lenses, eyeglass lenses, magnifying lenses, etc. Whereas with crystalline materials, they're typically opaque or translucent in their natural state. So of course, light transmission in amorphous materials is excellent, not so good in crystalline materials. Crystalline materials have excellent chemical resistance. Both of these materials will shrink in the injection molding process, more so with crystalline materials. So you can see that there's just some important differences to understand between the two basic groups of thermoplastics. There's also lots of fillers and additives you can add to these materials. So things like colorants, UV stabilizers, antioxidants, reinforcements, external lubricants, etc. And all these different things basically allow you to custom tailor a specific plastic for your end-use application. And the reason why it's important to understand the effects of the use of fillers and additives is that because number one, that different plastics have different properties and they process differently. So if we talk about polycarbonate versus polyethylene versus nylon, all of these materials have different properties. They all process differently. It's important to understand those differences when you're designing an injection mold. Within a class of material, the properties and the processability can vary drastically. So for example, you can have polycarbonate that's used to make DVDs. You can have polycarbonate that's used to make bulletproof glass. And we talked about fillers, additives, and reinforcements. They affect all of the above. So they're going to affect the processability and the physical properties of the material. I just mentioned polycarbonate. You see on this graphic here, I've got a DVD and bulletproof glass. So you take polycarbonate, very low molecular weight, very high flowing material, you can make a DVD. You take a very high molecular weight polycarbonate, very stiff flowing, doesn't like to flow into a mold, you can make bulletproof glass out of it. So it's just important to understand those kinds of things about the basic plastic material before you go ahead and design a mold. Very brief overview of the injection molding process itself. There's many advantages and benefits. Number one, you can produce complex geometry in net shape. That means when the part comes out of the mold, you don't have to do anything to it. You can ship it or you can assemble it to its mating components. It's a very high volume manufacturing process. We're typically talking about making hundreds of thousands to millions of parts per year out of one mold. It's a very fast process. The part cost is low, and plastics have many inherent advantages such as that they're light, chemically resistant, good strength to weight ratio, etc.
All right, before we move on, another quick poll question for everybody. For the plastic parts your company develops, how many rounds of mold rework are usually required before acceptable quality parts are achieved? 1, 2, 3, 4 more, or building boat anchors? So give everybody, that's Peter's favorite answer. So give everybody a chance to respond there. A few more seconds. All right, and looks like most people put 2 and 1, so only 6.5% use building boat anchors. So, all right, back to you, Peter. Thanks.
All right, thanks, Cliff. So now what we're going to do is, again, talking about best practices in injection mold design from a plastics point of view. Some of the high-level topics we're going to cover this afternoon. You want to maintain uniform wall thickness, follow some nice rib design guidelines we're going to present to you, gate from thick to thin, and minimize weld lines. So maintaining uniform wall thickness. Just to talk about some of your typical injection molding wall thicknesses, usually in the range of about 2 to 4 millimeters, or 80 thousandths of an inch to about 160 thousandths of an inch. Thin-walled injection molding, you'd be talking something on the order of about 0.5 millimeter in thickness, or 20 thousandths of an inch. The minimum limit for injection molding, it's about 1/4 millimeter or 10 thousandths of an inch. So you're not really going to see too many wall thicknesses below 10 thousandths of an inch. It's basically what we would call the kind of the psychotic edge. It's very difficult to go over that one. You want to maintain uniform wall thickness because that promotes uniform filling and packing. It helps you avoid flow hesitation. You can reduce the cooling time and maintain uniform cooling across the surface area of your part. It also helps you reduce material usage, which might lower your part cost. On the right-hand side of the slide, you can see kind of a worst case to a best case scenario, where at the top we have a very abrupt, sharp transition from thin to thick. And as you go down towards the bottom, you can see that we can, by adding a gradual transition and coring out the part, we can maintain a uniform wall thickness throughout. Rib design guidelines. A lot of plastic parts have ribs. The rib thickness, the base of the rib should be anywhere between 50 to 70% of your nominal wall thickness. Rib height should be about 2.5 to 3 times your nominal wall thickness. The ribs should have about 0.5 to 1.5 degrees of draft. That's to aid with part ejection. The base radii of the rib should be about 25% to 40% of your nominal wall thickness, and the distance between 2 ribs should be 2 to 3 times your nominal wall thickness. One thing that happens if you make a rib too thick at the base, you get a defect called a sink mark. A sink mark is where you have a localized increase in wall thickness. It shrinks more than the other wall sections around it. Because of that increased shrinkage, it pulls in the surface of the part, creates this defect that we call a sink mark. This just shows you here how we can use simulation to actually predict the likelihood of sink marks in your molded part. So we have a part here, we're showing the external view and the internal view, and you can see anywhere that we have an internal rib, we're getting sink marks on the surface of our part. This next slide shows you that as we decrease the wall thickness, simulation helps us to identify the fact that the significance of the sink marks decreases as we decrease the thickness at the base of the rib. Gating from thick to thin is basically one of the cardinal rules in injection molding. Top left-hand corner of the slide, we're gating from thin to thick. That's going to cause filling and packing problems in this part. On the right-hand side, we can add a blind runner. That might help us fill and pack the thick section a little bit better, but really the best way to solve this problem, lower left-hand corner, just simply turn things around and gate from thick to thin. And another thing you want to do is minimize weld lines. So weld lines are areas in the mold where two or more flow fronts come together. Weld lines can create both cosmetic and structural defects. You just want to avoid them as much as possible. You can do that by minimizing the number of gates or controlling the position of the weld line, making sure that it shows up in a non-critical area by changing your gate location. And of course, that's something that you can simulate using plastic simulation. With that, I'd like to introduce Solidworks Plastics. It's plastic simulation software. It helps you predict and avoid manufacturing defects, eliminate costly mold rework, improve part quality, and decrease time to market. The value proposition, it's simple and clear. That's because more than 80% of the plastic parts you touch every day are manufactured by the injection molding process. Injection molding is complex, molds are expensive, and oftentimes using Solidworks Plastics to avoid just one round of mold rework will help you justify the cost of the software.
All right, great. Before we get to the demo, another quick poll question. What plastic simulation software do you or your company use today? I'll give everybody just a few seconds to answer, then we're going to jump right into Matthew's demonstration. All right. And 83% do not use any software, so showing the results there. And on to the demo.
Let's take a look at Solidworks Plastics, an injection molding simulation software embedded inside Solidworks that helps mold designer predict and avoid injection molding manufacturing defects during the earlier stage of the mold design to avoid time-consuming and costly mold rework. We are looking today at a smoke detector housing, and we will study more in detail the top cover. The first thing you might want to do inside of Solidworks is analyze the part that will be molded. The draft is very important for a mold designer and is required in order to be sure the part will be ejected properly out of the mold cavity. With the draft analysis tool inside of Solidworks, you can quickly and simply ensure that the part was designed properly with sufficient draft. In fact, part without draft can get stuck or break in the mold. You can also use the undercut analysis tool to determine if costly side pulls will be needed in the mold. Once you are satisfied, we can move to Solidworks Plastics to optimize the plastic part design. After selecting the first configuration that we're going to look at, we can quickly and in just a few steps analyze the model. The first step, like other simulation tool, is to mesh the model. We can specify the meshing parameters manually or decide to let the software mesh this cavity automatically. Some parameters, like the triangle size for example, can be set up by entering a specific dimension or by using the slider. This helps to control the mesh density. We can also add some refinement to automatically use a smaller mesh for small features like ribs, holes, or higher curvature areas. You have a complete control over the density and the quality of the final mesh. Once the mesh is created, we can go forward with setting up the rest of the boundary conditions. The next thing to do is to select the plastic material. Mold designers can simulate the molding process very accurately thanks to the Solidworks plastic database that includes over 4,000 grades of commercial plastic materials. For this initial analysis, we choose a grade of polycarbonate. Polycarbonate is a very good material with great impact resistance, strength, temperature resistance, and good insulation capabilities. In fact, it's an excellent potential candidate for this particular application. The last step before running the analysis is to specify the gate location or injection location. Let's just pick an edge gate at this point. After meshing the model, selecting a material, and picking the gate location, we're ready to go and we can now run the analysis. As a mold designers, and to get even more accurate results, we can also change the meshing parameters such as the injection molding pressure and the mold temperature. After a pre-processing phase, you can see that the preview results are dynamically displayed on screen as the analysis is being solved. It's an extremely useful feature since it allows you to see if something went wrong in the earlier stage. We can then stop the analysis, fix the problem, and restart another one. The Plastic Manager also provides some great and valuable feedback for mold designers. You can know what percentage of the model is filled, the processing time, and what the maximum pressure requirements are, and instantly see if it exceeds your machine's properties. If you find out that the maximum injection pressure is simply higher than the maximum pressure of the injection molding machine, you will know that this part is unlikely to be manufactured properly without a design change, a process parameter, or maybe even a material change. As this analysis is running, the results are being generated. You can also see that we have a lot of different types of results that we're going to be able to look at. Not just the filling time plot, which can be seen on screen, but things like the injection molding pressure, average temperature, flow front temperature, or cooling time. Our analysis is now complete and we can look more closely at the results. But the first thing that comes up is what we call the result advisor. It basically explains all these different plots and gives you some advice on how to troubleshoot and fix any potential problem. To gain further insight, we can animate the fill time. Here we are looking at the profile of the melted plastic as it travels in the mold cavity. One of the major problems that we have here is a phenomenon called racetrack effect. That's usually caused by a relatively thick wall section where the plastics in one area of the part rests ahead of the flow front in the rest of the part. It may or may not be a problem, but in this case, like in a lot of cases, it causes backfilling that creates a lot of wet lines in these thin ribs. Wet lines are areas in the part where two or more flow front comes together. It's going to be very critical from a structural standpoint, and it's definitely something we want to avoid. We can also look at some of the results such as air traps. These are places where the air is inside the mold cavity before it gets pushed out. They can also indicate where the mold manufacturer or the mold designer should put the ejection pins to facilitate the air to escape. Other result plots also indicate a substantial cooling time of more than 60 seconds due to the thick area of the part. This will drastically affect the number of parts you can manufacture per hour and the overall cost of the part. Another critical information for mold designers and manufacturers. Now, using different configuration, we can analyze multiple variations of this part as we refine our design in order to find the best possible solution. In an effort to fix the racetrack problem, we decreased in this configuration the wall thickness in certain places of this part, specifically around the perimeter. With the same injection location and material, you can see that we ended up with another problem. Because we decreased the thickness too much, we created a short problem. No matter what you do, how you set up the machine, or how fast you inject the plastic, you just can't get the plastic to fill up 100% of this mold cavity. These molding parts will be nothing but defects. This new configuration features a slightly higher wall thickness. You can see from just looking at the fill time plot that we can now fill 100% of this cavity without reaching the maximum injection pressure of a molding machine. The cooling time, which is the time it takes for the part to cool to a temperature for which is safe to eject the part, is reduced significantly by more than 50%. It's because the wall thickness usually drives the cooling time. Cooling time is often about 70% of an average of the overall injection molding cycle time. This means that by improving the geometry of your model, you can reduce the cycle time and also lower the price of the part. Now, even if the part is being filled correctly, we still have problems with the weld lines being located in the middle of the thin ribs. In an effort to improve our weld line location, we change the gate location to another area of the part. The great thing about Solidworks plastic is that you can run these multiple what-if scenarios to see what's going on and how to get the less amount of weld lines and the best filling pattern. At the end, it's quite an accomplishment. The new injection location definitely helps us reduce significantly the weld lines, and we now pretty much don't have weld lines on those ribs. However, you can see that with 47 MPa, our pressure to fill is still somehow high. We still need to get this lower, considering that we are looking at a single part cavity, and the injection pressure requirements will increase when we move to a multi-cavity mold configuration with sprues and a runner system. Let's try to make a material change. We started with a straight polycarbonate and we're now switching to a polycarbonate ABS blend. It's very similar material in terms of properties and strength. But looking at our results, you can see that by switching to this new material, we managed to decrease by 20 to 25% the pressure required to fill the cavity, and that's going to help to more easily manufacture this part. Satisfied with this design and having overcome most of our initial challenges, we can now also look at the volumetric shrinkage. All these plastic materials shrink. That's why the volumetric shrinkage at the end of packing is more important. By changing packing pressure and time, we can actually affect what our volumetric shrinkage is. Overall, we've reduced the volumetric shrinkage from the 10-12% range down to 1-2% range after packing. Also, we have a much more uniform distribution with no significant differences from one end to the other, so that's highly unlikely that the part will wrap or deform out of shape when it comes out of the mold. Now that we optimize strength, chemical resistance, and even the same color and surface appearances. However, one of the problems is balancing the filling so that all the different cavities fill at the same time and at the same pressure. It's virtually impossible to figure out how to do that without the help of Solidworks plastics. Within Solidworks plastics, you can use a runner balancing analysis tool and specify some parameters like the runner segments you want to vary. Then the multi-iterative analysis will figure out what size those runners must be. Switching to the last configuration, you can see that the runner system was balanced and now all 4 cavities are filling approximately at the same time. As you can see, Solidworks Plastics is perfect to optimize your plastic part and mold design to come up with the best possible solution. It's an invaluable tool for any mold designers, and packed with many useful features and tools, including report capabilities, it's easy to communicate your result to customer or the member of your organization. Solidworks Plastic will definitely ensure your mold works the first time.
Thanks, Matthew. Great job on that demo. So to summarize, remember what we talked about here is that it's the best practices in injection mold design from a plastics point of view. You want to maintain uniform wall thickness. So if you, as a mold designer or mold maker, if you inherit a part design from upstream that's got a lot of abrupt transitions from thick to thin, that's not a good thing. You know, even though you can design and make a mold with those, with those things in it, it's not going to be good news when you get to the molding machine. You want to follow those rib design guidelines that we presented. Always try to gate from thick to thin as much as possible and minimize the weld lines in your molded part. And regarding Solidworks plastics, by using Solidworks plastics during the earlier stages of injection mold design, It helps you to predict and avoid injection molding manufacturing defects, eliminate that costly mold rework, improve your part quality, and decrease your time to market.
Excellent. Thanks, Peter. I know there was a lot of information. We ran a couple minutes over, but a couple more poll questions while we actually take some questions. Peter, if you want to answer a couple of these questions here. What category do TPEs fit into? Oh, sure.
So we'll start blowing through the questions. So TPEs, thermoplastic elastomers, they're actually composed of both crystalline and amorphous regions, but I think you would generally characterize those as crystalline materials. And of course, as a thermoplastic, they're they can be heated, melted, formed, cooled down, reheated, formed, cooled down, and so on. That's one of the inherent characteristics of thermoplastics.
And if you notice, I added one more poll question up there. What is your level of interest in SolidWorks plastics? This, let us know if you need any more information. I'm going to go on to the next poll question, which is, would you like any further information from us? If there's anything you need, you want a SolidWorks reseller, a demo from a reseller, or quote information, etc. I'll leave this up and let Peter answer some more questions here.